that review sheet. I've broken my screen up into 4 sections. We've had a bunch of units so far, but there's been a lot of repetition. When it comes to solving problems, your problems are going to run the gamut of all of the units. But we really have 3 major principles that have been part of our discussions. There's dynamics, Newton's laws. There's work and energy, including conservation. And there's impulse and momentum. Including collisions. At the same time, there's also been kind of some ancillary materials. Things that support the others. In fact, our first unit, I would say, is all ancillary. I was desperate to get out of it. You guys were desperate to stay there. But you understand now why I really didn't want to spend any more weeks on kinematics. Do you see now why? You just wanted to nail it, and you were so used to things being memorizable. It was just not the best. It still isn't. The question comes down to when you're looking at a problem, where should you go? Some of these are more adept at handling certain questions rather than others. It should be clear to you that Newton's laws were used to develop the concept of work and energy and develop the concept of impulse and momentum. But what you should have found through the course of our discussion is that some of these problems are easier to deal with when dealing with perhaps energy or momentum than Newton's laws. At the same time, some problems can only be handled with one of these, while other times we have found there might be more than one way to do a problem. So let's consider the strengths of each of these. And oftentimes, determining this comes down to what are you being asked to find. Newton's laws are great about finding individual forces. They're good about finding acceleration. Probably the only way you're going to deal with issues of friction. Right? Also, a good place to start if you're supposed to set up a differential equation. And this is because we're dealing with the sum of forces, which equals ma or 0, depending on the circumstance. I know there's Newton's first law and Newton's second law, and they are obviously separate, but Newton's second law and Newton's first law are consequences of each other. If the forces are balanced, there is no change. If the forces are unbalanced, there is a change. I would lump into this, though, that torque and force really represent 2 sides of the same coin, same topic. However, that's it. That's all Newton's laws can really do for us. And although there's more application of Newton's laws, if you want to find out anything else about a problem, you'd have to extrapolate from acceleration. Right? If you want to know how fast something's going, how long something takes, how far something goes, you'd have to start with acceleration and then develop a model of movement from acceleration. This is where you would say like motion equations, but I caution you, because when you say motion equations and I say motion equations, we mean different things. You would probably say a motion equation is something like v equals at plus v naught. It's not a motion equation. A motion equation is acceleration is defined as the rate of change of velocity. And velocity is defined as the rate of change of position. This is what you must do to get a motion equation. You solve Newton's second law, get an expression for acceleration, and then use calculus to find an expression for velocity and an expression for position. The special case is if the acceleration is constant. If the acceleration is constant, You have a polynomial function in which you can get an expression for acceleration that is, expression for velocity that is linear, and an expression of position that is quadratic. I won't write all 5 of Galileo's motion equations here because they're not all motion equations. Technically, a motion equation tells you about something in the future based on initial conditions at the present. So if you look at both of these, they have initial conditions at present. V naught, A, X naught. Initial position, initial velocity, initial acceleration. And they predict a future location. They predict a future velocity. You plug in the time. But we know that there are other motion equations. Right? We're aware. And we've even had other motion equations. Things that are more complicated because we've had differential equations that have shown that sometimes the velocity is complicated, like an object experiencing drag. So Newton's laws are good at this stuff, but require a lot more if we want to find anything out about velocity, position, or time. Work and energy was kind of a way around it, and not so much around, but a way to deal with problems that maybe didn't fit so well into Newton's laws. Perhaps the acceleration is changing, like a ramp that instead of being flat is curved. Instead of having to deal with the curvature of the ramp, we just looked at the change of height. Remember stuff like that? We developed this idea that if nothing was lost due to friction or air resistance, then the change in potential energy would have to be equivalent to the inverse change in kinetic energy. If the potential energy increased, usually the kinetic energy decreased, right? This is a statement of conservation of energy. You add up all the energy you have before and set it equal to all the energy you have after. How can you tell if you're supposed to use something like this? Well, we tended to look for things like changes in height, compression of a spring, and change in speed. Conservation of energy was really good at telling you how high something went, how fast something was going, and how far the spring was compressed. Right? It used different versions of potential energy and different versions of kinetic energy. Yes, there's more. There's the work energy theorem. There's a definition of work. There's work done by individual forces. All of that's there. But when you're on the spot and you're trying to find a way to solve your problem, we look at the big picture here. Yes, if you're asked to calculate work, find an expression for work. There's only 2 ways to calculate work. You either do it directly by the work done by all the forces, or you recognize that work can be equal to the change in kinetic energy. I can't write those down, but here, we know that work equals the integral of f dot dx, force times distance, and net work can be equal to the change in kinetic energy. The entire time we've had motion equations, we've had something else in front of us. I wouldn't write this down quite yet. Let me just manipulate it a little bit. I just subtracted V naught from both sides and switched sides. Is that okay? What if I know the mass of the object? I can multiply through by the mass. Correct? We can do a little regrouping here. Good so far? Net force times time equals the change in momentum. It's always been that motion equation the whole time. But here is really a critical look at it. Because this function, the definition of impulse, doesn't require a constant force. It requires just understanding that the net force times time will equal any change in momentum, and it's a vector quantity, so it takes direction into account. Unbalanced forces cause changes in momentum. That's what it says. But really, what do we use momentum for the most? Collisions. The change in momentum of one object has to be equal to the change in momentum of the other object. It is Newton's third law. The thing missing from over here, a direct consequence here. You cannot touch without also being touched. That's what it's saying. You push on something, it pushes on you. You give something some momentum, it takes it away from you. Collisions is what you look for here. If there's a collision, you go for momentum. Momentum is the most likely place that you're going to work. Now, again, you have to look at a problem and within a couple of seconds figure out a direction you're going to go. All I'm providing you is, look, if you see something in the problem, pick the most likely place to solve it. There might be other ways to solve these problems. And with all of these, we have to add to it the idea that there's also angular momentum. The change in angular momentum from one object has to equal the change in angular momentum of another object. That would be an angular momentum collision. We also have the idea that an object can change its configuration. I'd call this an ancillary. That there's moments of inertia. The integral of r squared dot dm. And center of mass. That's out there too, right? X center of mass is a ratio. You can't see it because of that label there, so I'll just put it over here. Of the sum of r dm divided by the entire mass. What's another ancillary piece of information? Well, what if the force is causing something to change its direction? Well, then probably you're going to be using v squared over r, or omega squared times r. In fact, I'd argue that the only way to deal with something traveling in a circle is to use forces, UCM. That's back there at dynamics. What I've just tried to give you is a simple cheat sheet to look at a problem and from there maybe find the fastest way to attack it. It's not an exhaustive list, mind you. It doesn't tell you how to use these things. For that, you should confer with your notes. We've done all the examples. How do we know if an object is in simple harmonic motion? Today we're going to do a new object, a different object. I want to just assume we have some random object, whatever that is. That's our thing. It has a moment of inertia. This object, some random thing, has a moment of inertia, I, has a mass of m, and let's say that its center of mass is located right there. The x marks the center of mass. In fact, we're going to fix it in place at a pivot point here. And I'm going to draw an arrow from the pivot point to the center of mass, and I'm going to say the length of this arrow, x, is the distance from the pivot to the center of mass. If I take some random object and set it into uniform circular motion, uniform circular motion, what am I saying? If I set it into some kind of oscillatory motion, I want you to be able to determine, theoretically, if that object is in actual simple harmonic motion. The first step, and it sounds silly, is the object oscillating. So the object oscillating under the current conditions.
Please pardon me.
So, the next thing you should do is when you displace the object, will there be a force that will attempt to return the object to equilibrium? If you believe so, then your next step, and the most important step, is to model that force. And I'm going to say this as clearly as I can. Model that force or forces. And I'm going to put in parentheses, torque or torques. Using Newton's second law. And then does the model match the generic expression for an oscillator? Meaning sub in for the acceleration, dv dt and dx dt. All right.